So, welcome guys, it's my pleasure to wake you up today to get us started, and I hope I can do something by providing my presentation with you. So my topic actually is about inspection and site surveys, and I was asking myself about the fact that especially large-scale utilities, they are placed far outside, they're not next door, right? They are placed in rural areas, they are off-site, they are offshore probably. And there are always challenges of logistical efforts. You have to get there, you have to spend money, time is always limited doing inspections, and of course there are weather conditions, right? Because why do we choose wind energy sites? Because there are a lot of wind. And I was thinking about how can you cope with these challenges by bringing your site into the office, by just digitalizing what is on site. And that's what I wrote my master thesis about, and that's what I would like to introduce you, including some results from field tests that we were doing afterwards. First of all, the main motivation, the main factor is about risk management, right? It's about risk mitigation. In particular, projects are facing completion risks. Because if you do not have sufficient information about what's going on site, how is the site developed, how complex is the ground, how can you plan for construction, logistics, and so on, there is a certain risk of completion. I will go into detail regarding offshore wind energy in Germany that we experienced a few years ago about completion risk. There is also, of course, a technology risk, because you know all the dynamic loads on wind farms, for example, they are challenging. It's a big challenge for the technology and for even for the civil engineers that are working on site. And of course, during operation and maintenance, you want to reduce outages, because availability is what matters. And I'm not going for the third one. I'm not showing again all the slides. You already know how important financing and costs are for renewable energy projects, right? We all know, we have learned it, we have seen it a few times. And of course, all the outages, all failures of components on site means a commercial risk for your renewable energy project. And some things I would like to tell you today, they are about lowering those risks. First of all, who gave me the idea? A friend of mine, he's a professor at the University of Dresden. He's doing some research on a photogrammetry algorithm that's called structure from motion. And he was working in an informatics section of his university, but with the archaeologists. And archaeologists have the problems that they are working mostly off-site. They have to document their findings, they have to document their sites where they're doing exhibitions and so on. And as usual, their budgets are very limited. So they cannot afford to rely on high-cost technology like laser scanners or like sonar scanners or so on. So they need some low-cost solution. And that's the interesting part. They developed a low-cost solution that you can utilize with any commercial drone or any commercial software, open source software that's available on the market. So in contrast to all the high technology stuff like LIDAR or multi-beam technologies that are in use today, they all have one thing in common. They are very accurate, but they're very expensive. And if you ask yourself, how can you utilize a low-cost mechanism? They developed a tool chain to actually provide the same results based on photographs or videos, which is called photogrammetry or videogrammetry. So I thought, okay, I would like to look into this and to see where can you apply it in renewable energy projects to exactly gain what I just said, to know what is on site, to create data models, to bring your site or the installations on site into your office. I won't go into technical details here, just that you get an idea of, you start with a recording what's on site using pictures or videos. You have to extract a certain key frame of pictures that are showing the results of your object of interest from any kind of different perspective. Then you start a reconstruction using specific software, and there are a variety of software on the market, from really expensive ones but until open source software. Everything's basically available. And then you create something that's called a point cloud. And the point cloud is actually a 3D model of your object or of your site, where different pictures from different perspectives identify the same point. So that's why it's called a point cloud. Using that point cloud, you can do pretty much anything in a CAD or a GIS application. You can create like a georeferenced model to upload it into your GIS. You can create a CAD model to provide it to the planner to have a look in a detailed way on the objects. And based on that tool chain, I try to make up some use cases, particularly for wind energy, where you can actually look into this tool chain, look into this technology, and to see what are the benefits that you gain. Just to give an idea, this is how they create the pictures, right? So if you take two pictures from different angles showing the same point, then you get an idea of a 3D model. It's like you can try the same with your thumb. If you hold your thumb right in front of you and just change your eyes left and right, your thumb will go like this. That's because you get ideas. That's the same way our brain works, actually. You have two eyes, you get two different angles, and your brain creates a 3D model of it. And again, the really good thing about it, it's a really standard drone. It's not even 2,000 euros. It's not like a 40,000 euro laser drone that you have to comply. All right. First of all, one field test that we do was with a company located in Bremen, in Germany. And they asked us to get into their nacelle to get some pictures, get some models of their installations on site. Thing is, we learned they gave us just a really, really crappy video made by an iPhone. They were running around like this. And first, when I saw this video, I thought like, oh, there's no way. We have to go there. We have to provide professional lighting and good photographs. But we tried. And I was wondering, because at least we were able to recreate some parts of the installation components on site. For example, here you can see the point cloud, and you can see an electrical connector that is installed inside. You can also see the weaknesses of this technology, because it's not quite accurate if you do not care about lighting and so on. So if you utilize bad pictures, bad videos, the quality of your result might lag. So lessons learned from this field test is you really have to prepare for that site. You really have to know what is on site, what are you trying to capture, and what kind of photographs do you need to take, and what's the quality of that photographs. But use case one for this kind of technology would be to get an idea of detailed objects on site. It could be something that's already installed. It could be something that you want to further inspect when planning your wind farm site, like a bomb, like a coral reef offshore, like anything that you need to provide for environmental protection, and so on. All right, next use case is actually to survey the entire site. That's something we did for a wind farm company in Lemgo. I don't know if you know Lemgo. Lemgo is quite a complex area. It's nothing compared to Switzerland or Italy, but still it has its hates, right? So it's not easy to plan a wind farm site when the ground goes like this, because you have to prepare. You have to know, okay, what are the construction purposes? How's the ground? How about the roads for the construction trucks and so on? Is there enough space to bring 40 to 70 meters long blades on site and so on? So what we did is we went on site to took pictures. All the blue dots are pictures that we have taken from the site using a standard drone I showed you before. And we created and generated a 3D model out of it. It's actually hard to see because it's a 3D model printed to a 2D picture. But we were able to generate a 3D model of that site. and gave it to the planner. So he imported this to his CAD application and provided construction planning, planned the roads, the access roads, and so on. And we also created an auto image for the GIS people. So there are two different stakeholders, two different people, having their own use cases, but both could participate from the results that were created on site. Second example, I haven't tried it, but you remember hydropower, right? I took the slides from Katie from the on-campus time 3 years ago. You might remember the power equation formula. And we remember the power that you might get from a plant, hydropower plant, requires on the height. So it's essential to know the accurate height. Because imagine all the power that you calculate from your power plant. It will have an influence on financing, on anything, on a cash flow model, anything you need to cope with commercial risks, to cope with financing. And imagine if you have a complex site and no information about the site, there's no measurement available. You need to know what's the height between the powerhouse and the reservoir, right? So resource assessment is always necessary, and by utilizing this technology, I'm sure you can save a lot of time and effort by doing this site survey. So that would be another use case for site surveys and renewable energy projects. Okay, and the third use case, I extracted it a bit, is about offshore wind energy. Before I go into details, I would like to tell you something about the one offshore wind farm that was planned in to go in operation in 2013. It's called Riffgard. I don't know if you heard that story. Right in Germany, north of Germany, North Sea. It's like they build a big wind farm offshore, and in 2013 they completed. They were happy. They wanted to start. There were gigawatts of power available, but there wasn't any grid connection available. So imagine there's a huge wind farm running offshore in the North Sea, but there's no grid connection to use the power. Maybe you remember there was a really big trouble about it. So people were fighting about money. There was a damage of around 80 million euros. Politicians got involved, anything, because TenneT wasn't able to provide a grid connection in time. At the end of the day, guess who paid for it? Who knows who paid for it? For the damage? The German consumers on their electricity bill, saying, oh, there's a special fee for renewable energies now. And everyone was like, oh my God, your renewables, they are so expensive. Because we paid for the risk at the end of the day. Now, I know these problems are complex, and I'm not saying there's only one root cause for it. But certainly, one major root cause was TenneT was lacking information. Because what they discovered by rolling out their offshore grid connection, they discovered bombs from World War II. So they had to stop their rollout. They had to bring experts in to clear the area, continued, discovered more bombs, had to stop, bring the expert in, and so on. They were just lacking information. They had no idea what's down there at the seafloor. Of course, they used sonar, and they have large boats, large ships that provide a survey of the seafloor, but they don't see. They just get an idea of the seafloor model. They don't actually see, they have no visual information like you get from a picture. Right? So nobody really saw that there are a lot of bombs from World War II at the ground. Same applies to if you discover like corals or anything that needs to be protected. So when you're planning a wind farm or a grid connection, of course, you have to make sure that you do not destroy natural habitat, right? So they have to provide an environmental impact analysis or assessment to document and provide evidence that you are not destroying anything that should be preserved. So what I'm saying is anything that works with a camera drone, of course, works with an unmanned underwater vehicle as well, because at the end of the day, it's all pictures that you need to create. Saying that, it's not that easy because of course, you have to make sure that the images you get are enhanced because you get absorptions and so on. You get a lower quality of pictures. And I'm saying the use case I'm talking about now is about really knowing what's going on at the seafloor. And of course, during operations and maintenance phase, there are regular inspections of the foundation, of the grid connection. You might want to prevent the foundation, for example, to create potholes, and so on. And that's something I will go into detail on the next slide. There is also, I think, a huge potential for autonomous inspections by self-driving UUVs. I brought you one example. Again, it's just one study. I know there are a variety of studies on the market around offshore wind energy. I just picked one. I'm not saying that's the best or whatsoever. As you can see, they did a research on what are potential innovation trends in offshore wind energy. And you see, apart from some weird designs, they say that during the next 10 to 12 years, they're expecting to become more autonomous. They are expecting to really increase the mode of automation, to have use of robotic inspections, to have use of autonomous UUVs, to really automate all inspection tasks around offshore wind energy. So just imagine if you have to, for example, if you have to inspect your foundations offshore twice a year, if you send down divers, they are basically risking their lives because it's offshore. It's an electric installation. There is a strong current, there's weather conditions, anything. So it's not just about money, it's about the safety of the people. And once again, they are forced by law to do so. So if they are able to save money every year by having autonomous UUVs that are doing the inspection for them, I think that's one of the most interesting ideas of that SFM use cases that I discovered so far. Again, as you can see, it's all really based on wind energy and a bit hydropower. That's because I wrote my thesis particularly for wind energy. But I think you can apply this model to any project that you're planning, as long as you have to. Doesn't matter if you have to plan a large CSP site somewhere in the middle of nowhere, or if you have to plan a wind farm somewhere. You can apply this technology, and I think what I'm saying is if you utilize this structure for motion technology, it allows you to bring some parts of your site into the office, to give you time to do the right decisions, to plan your site visits. Of course, it does not replace the site visits. It's not possible to replace it. But it gives you, as I said, it gives you the time. There is no weather conditions in the office. There is no time pressure. You can do the right decisions, and you can do a better preparation of your site visits. And again, structure from motion is really a low-cost alternative. You saw some examples. In some cases, it lacks precision. It's not as precise as if you, for example, use laser. But on the other side, it gives you some visual information, some pictures, something you can really, as a human being, you can really understand what's going on there. And of course, these are just two examples that I did within a few weeks. And of course, there is a lot of potential to get into details, to work together with operators and planners to see what are their use cases, what are their challenges, what are their interests in really getting to know what's on site. And that's why I think there is also a lot of topics that is worth looking into. For example, doing research in autonomous underground vehicles, work on some simulation parts, because all the 3D models that are created can also be uploaded to a virtual reality or augmented reality. Just imagine you're on site with a public community, showing them on a tablet how their future wind farm would look like on their real landscape, not on some landscape that was made up by the designer, but a real landscape they get to know, right? So it could improve public acceptance. There are some ideas around trend analysis for construction monitoring. So if you, for example, if you get a regular report, 3D model of your construction site, you can do a trend analysis. How is it developing? and are we still on track with the schedule and so on. And of course, if you apply some algorithms, some feature detection algorithms, you are even able to detect defects like cracks in the foundations, like oil at the wind farm nacelle or something like that. But again, this would require a really, really strong cooperations with the planners and operators of these projects, because they know what to look for, right? Okay, thank you very much. I'm now open for any questions.
Thank you very much. That was very interesting. It is particularly interesting about the future research using augmented reality.
Yeah.
I think that's something that we are going to see in many fields, using augmented reality for our better purposes. So have you discussed this with project planners? Do they see a value in this type of approach?
Yes, actually, they see a huge value. When I did my studies or research for my MBA thesis, I did some interviews, and funny thing is, if you ask some operators around Berlin or the surrounding area, it's not complex, it's all flat. So if you ask them about 3D models of their environment, they're like, no, we don't care, we use maps, right? Because it's not complex, it's all flat, there is no risk of construction planning. But the same people told me, but if we would be able to provide the public communities with a 3D model of our planned wind farm, or like an augmented or virtual reality solution, it might really improve our project, because we are always struggling with the public communities. They just won't accept it. They are too pessimistic about wind energy, and they get no feeling about how will it look like later on. So yes, I think there is a huge potential especially for that purpose.
Yeah, I think even if you use exhibition hall where people can come and wear the virtual reality or augmented reality headsets and see for themselves how it looks like, that's going to make a big impact on acceptance.
And the second example would be training centers for offshore, because at offshore maintenance or offshore construction sites, different companies with different specialties come together, and it needs to be coordinated, right? So it's worth having like a virtual training center where they can practice their on-site activities.
Right. Thanks.
Yep.
Very interesting. Open for questions.
Okay. Hi, John Quill.
Hi.
Really interesting presentation, thank you. So I work for Infosys, and we do augmented reality and virtual reality for digital oil fields for exactly this. So how you can evaluate and do predictive maintenance and then send down drones, etc., to fix accordingly. Do you do this as your day job as well? Because it'd be interesting to just join up with combination.
Let's just say, as part of my responsibility is to work on innovation, and we are not really market ready, but we have some good connections to offshore wind operators, and we are trying to get something started, some new projects to especially work on underground vehicles to support their maintenance activities. So certainly, yes, I'm very interested in cooperating, but it's really at the beginning of everything, right?
Okay.
It's just,
That's good.
Any more questions?
This way. You mentioned the second World War bombs on the ground of the sea. Can you tell us something about the vessels to use to detect them? Because if I got you right, you won't detect them with a drone in the air. You have to use a different vehicle in the sea. What about an entry price level for such a vehicle?
I don't know. I have no idea how they clear it or detect it. I know that in order to detect them, of course you need a metal scanner. But the metal scanner doesn't work from the surface. You have to go below the sea surface. And the second problem is they already do surveys of the seafloor. And they have even better technology. They have multi-beam and so on. They look right into the sea ground. But the problem is they don't see any pictures. Computers are fine with that kind of stuff, and they create a really nice bathymetry or anything, and you get an idea of how is it structured, but you actually don't see what's down there because we don't have no pictures. That's our weakness as a human being, right? We need to have, we're visually focused, and we need to get pictures. And I think, so to answer, I think, of course, you could enhance this technology by having metal scanners on the underground vehicle, but I think you can also gain benefit if you just have a plain picture of what's down there. Or maybe even a 3D model to detect is it shaped like a bomb or is it shaped more like a stone or whatsoever.